double prime plus by prime plus c equals 0 represents what? The harmonic oscillator. Okay. And what's the characteristic equation of the harmonic oscillator? Yeah. It's as squared plus bs plus c equals 0. And if b squared minus 4km is less than 0, oh, that's fine. Yeah. So this basically is the thing under the radical of the harmonic oscillator. If it's negative, we call it underdamped. True or false? True. Okay, so there's nothing brand new in today's lecture. We're just sort of pulling lots of bits and pieces together that we have looked at in Chapter 2 and Chapter 3. And we're going to talk about the harmonic oscillator a lot. All right, so the harmonic oscillator, my double prime plus by prime plus ky equals 0. M positive is the mass, K positive is the spring constant, and B bigger than or equal to 0 is the damping coefficient. Sure. Yep. And the equation is said to be second order, linear, and homogeneous. So thus far, we've developed two ways to solve this thing. And actually, you had a question like this on your test. And you could have solved it either of two ways. We could do lucky guess, which we introduced in Chapter 2. Or we could convert this to a linear system and solve by finding eigenvalues and eigenvectors. So let's do it both ways. Short way or long way first? You want to convert it? All right. All right, so if I convert this to a system, you make y prime equal to v, and then v prime would be negative 7v minus 10y. Because v prime is actually y double prime, so you solve for y double prime and replace the y prime with a v. Then we write this in matrix form. So I'm going to say y prime, v prime. Many people like to do v prime, y prime. It doesn't matter, as long as you keep everything consistent. Yep, so my matrix is going to be 0, 1, negative 10, negative 7. And if you did Vy, your matrix will be switched around a little bit. Yep. All right, so now we have a linear system. It's written in matrix form. If you want to solve it, what's the first thing you do? Eigenvalues, right? So we do the determinant of a minus lambda I. So this is going to become 0 minus lambda times negative 7 minus lambda minus negative 10 equals 0. Everybody know where that comes from at this point? I didn't write everything out. All right, so if I distribute my negative lambda here, I'm going to get lambda squared plus 7 lambda plus 10 equals 0. And does that factor? 5 and 2. So I get lambda is negative 5 and negative 2. So now I have eigenvalues. What do you need after eigenvalues? Eigenvectors. Yep. So I'm going to try to solve AV equals lambda V. So A is 0, 1, negative 10, negative 7. V is some unknown vector. That's the eigenvector I'm looking for. Negative 5 xy. And this will give me equations. So this says that y has to equal negative 5y. Yep, so 0x plus 1y has to equal negative 5x. Sorry. So if I pick a vector, pick an x, maybe 1, what would y be? -5. All right, so then I do the same thing, but instead of putting a -5 there, I have to put a -2 there. So again, I'm going to get y equals -2x, and my vector for that one would be 1, -2. All right, so then I take a linear combination of my straight line solutions. Each straight line solution is e to the lambda tv. So my final vector valued solution that includes a y and a v. In fact, I think I'll write it like this. Y, v equals k1 e to the -5t times the vector that goes with -5, which was 1, -5, plus k2 e to the -2t times the vector that goes with that, 1, -2. So I have just come up with two functions, y of t and v of t. But really, I only want a y. I only want y because, well, I didn't specify. But the solution to the differential equation, a second order differential equation, is just the y function. So I just would write y of t equals, and I just want the top component because I have y on top. If you put v on top and y on the bottom, then you would take the second component. So this would be k1 e to the -5t plus k2 e to the -2t. So that's the chapter 3 method, where we turn it into a linear system and solve using eigenvalues and eigenvectors. Did you not need this after all? Okay. All right, and what's the other method? Yeah, you make a lucky guess where you say, okay, I'm adding 3 functions together, right? A y, its derivative, and its second derivative, and I'm getting 0. So these 3 terms have to be alike. I have to be able to add them together and get 0. So what kind of function would be a like term with its derivative and its second derivative? E to the, yeah, right, natural log, its derivative would be 1 over. Yes, it wouldn't be the same. But so we might guess that a solution would have the form y equals e to the st. And that means that y prime would be se to the st, and y double prime would be s squared e to the st. And then we plug all those things into the equation and figure out what s has to be to make it true. So y double prime is s squared e to the st plus 7y prime. So I put my 7, my y prime is s e to the st plus 10y, which is just e to the st, has to equal 0. I can factor out an e to the st, and I'm left with s squared plus 7s plus 10. Does that polynomial, that quadratic, look familiar? It's the same one we solved when we were finding eigenvalues, right? So that is actually the characteristic polynomial for the equation. So we already know s is going to be -5 and -2. So now that means we have found 2 particular solutions, right? E to the -5t and e to the -2t, because we guessed that they would have the form e to the st. I have 2 different particular solutions, so my general solution would be a linear combination of these. Okay, so now that we found the general solution, I want to find the particular solution that satisfies the initial condition y of 0 is 2 and y prime of 0 is negative 13. So let me just write down the general again. It was y equals k1 e to the negative 5t plus k2 e to the negative 2t. I have two unknowns in there, two unknown constants, which means I need two initial conditions. So they gave me y of 0, which will be k1 plus k2, has to be 2. And then they gave me y prime. So let's take y prime, which is going to be negative 5 k1 e to the negative 5t minus 2k2 e to the negative 2t. And we also could have gotten that from the v. If you had done the chapter 3 method, you would have had this already because you found y and v. And y prime is the same as v. So then y prime of 0 is going to be negative 5k1 minus 2k2 equals negative 13. We do quick substitution. K1 is 2 minus k2. So I've got negative 5 times 2 minus k2 minus 2k2 is negative 13. Negative 10 plus 5k2 minus 2k2. So this is 3k2 equals negative 13 plus 10 is negative 3. So k2 is negative 1. And that means that k1 is 3. So you do have to be careful not to just circle the values of the constants and move on. You got to, when they're actually asking for a solution, so you got to write down a function y, replacing the k1 and the k2. Minus 1. So that would be your final. So we have developed this nice shortcut for solving a linear second order ODE. You can just immediately convert to the characteristic polynomial. And let's go back once really quick. The other thing that you might notice about this characteristic polynomial is that its coefficients are 1, 7, and 10, right? And if you look at the original ODE, 1, 7, and 10, you didn't even have to do lucky guess, right? We could have just written down the characteristic polynomial and solved it. So that's what you're going to start doing in the class activities.